Hello, and welcome to lecture number 10, part 2. In today's lecture, in this part, we're gonna cover section 7.4 from the book. 7.4 is a little bit different. Previously, we learned how to count. Yes, I understand. And now, this time, we're gonna understand and apply factorials. And then we're going to analyze set problems. And by sets, I mean problems using sets, using permutations and combinations. And all of these things will be defined in what we're going about. So let's get started. Permutations and combinations. Before we do that, we're going to look at something called a factorial. So previously, just above, we looked at how many different ways there are to multiply things together. And one of the things that we came upon was, I believe it was 10 times 9 times 8 times 7. Now, this sort of thing gets used quite a lot. In fact, it gets used so often that we define a mathematical function called factorial for it. So we define a factorial for any natural number. Natural number means it is a whole number, a counting number, like 1, 2, 3, 4, 5. So it has to be one something like that. So we defined that as n factorial is equal to n times n minus 1 times n minus 2, all the way until you get to 2 times 1. And then we define also 0 factorial is equal to 1. And there's a reason that we do this, and we're going to need something like this when we're doing division. You don't want a 0 in the divisor, but it works out that way. And then we also have that n factorial is equal to n times n minus 1 factorial. And we'll put these in more terms that you might be easier to understand. And we'll look at the number 10 as n. So if we let n equals 10, 10 factorial is equal to 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, believe it or not, your calculator probably has a button for that purpose, and mine, in fact, is right here. And in fact, this button is also going to be used when we're dealing. Let me see if we'll change the zoom on here, and then we'll change it back. So this is my button. So I've got a factorial, and then these other two symbols are the ones that are used for, there we go, for combinations and permutations. So 10 factorial is a rather large number, by the way. It equals 3628800. So 10 factorial is equal to 3,628,800. Like I say, a rather large number. So this is a number that grows very, very fast. It's also equal to, so 10 factorial is also equal to 10 times n minus 1, looking at this, which is 9 factorial. Which actually kind of makes sense. We're just 10 times 9 times 8 times 7 times 6 times 5 times 4. And we'll do some examples. For the most part, these are pretty straightforward, but some of the division stuff gets interesting, okay? And here's why we say this. So 4 factorial. 4 factorial is equal to 4 times 3 times 2 times 1. Now, typically, I'm going to omit the 1, basically because it's just the same. So you have 6 times 4 is equal to 24. 9 factorial divided by 8 factorial. Now remember, we were able to do this little trick. Well, that means this equals 9 times 8 factorial divided by 8 factorial, which is equal to 9 times 1, which is 9. So that's why I'm going. This is actually a very, very useful thing to do. And we'll do it quite often, in fact. Another example is 16 factorial divided by 13 factorial. Now, the advantage of doing some of these things with factorials is, first of all, the notation doesn't take up much space. But you can also expand, so this would be 16 times 15 times 14 times 13 factorial. And divide this whole thing by 13 factorial. So this equals 16 times 15 times 14, which equals 3,360. Now, some of these seem like large numbers, but when we're dealing with probability and statistics, they're not necessarily. We'll do one more example. Okay. So this is a little bit different. So now we have 32 factorial divided by 4 factorial times 31 factorial. So we know that (32 factorial) is equal to 32 times 31 factorial. I'm trying to understand what I'm doing here. Sorry. And that's, I'm not quite sure what I'm doing there. Okay. So 4 factorial is 4 times 3 times 2, and then 31 factorial. So we know that, I've got a typo up there, sorry. So we end up with 32 divided by 4 times 3 times 2. That's equal to 32 divided by 4 is 8. 8 divided by 6, which is equal to 4/3. I'm just going to correct this typo. I'm not quite sure what happened here. So this should be 32 times 31 factorial divided by 4 times 3 times 2 times 31 factorial. And that equals to, I'm going to 32 divided by 4, which is 8. So 8 divided by 6, which is equal to 4/3. Okay. From factorials, we go straight into permutations. So permutations is, say we have a set of shapes, 5 shapes in this case. How many different ways can these shapes be arranged? When we say how many different ways can they be arranged, we know that we have 5 shapes, so the order is what we care about. Now, if we think about it, going back to the orders, the way we can do something, we know that it should be, well, if we pick a shape, we have a box, a bag of 5 shapes. Pick one out. That's 5 possibilities. Now there's only 4 left, so it's 4 possibilities. Then 3 left, then 2 left, then 1. So that tells us that it is, in fact, 5 factorial, which is what we're saying right here. So we have 5 factorial, different ways of arranging these 5 shapes. Now let's say that we have the 5 shapes, but we're only interested in using 2 of them. Well, there's a couple different ways we can say this. So, and how we say this is a permutation of a set of n distinct objects taken r at a time without repetition is an arrangement of r of the n objects in a specific order. Okay, so we know that we're only going to pick 2 shapes this time. So we have 5 possibilities for the first one and 4 possibilities for the second one. So it's 5 times 4. That's how many possibilities there are. But where we denote this a little bit differently. And we're going to denote this with a term n permute r, which is equivalent to 5 times 4. And this is absolutely correct, and you can certainly do it that way. However, we'll notice that these two terms are exactly the same. So this is equal to 5 times 4. But now we have 5 times 4 times 3 times 2 times 1. So that's 5 factorial divided by 3 factorial. So the number of permutations, so n permute r, or in this case, 5 permute 4, I'm sorry, 5 permute 2, I said that wrong, I apologize, is 5 factorial divided by 3 factorial. Now, like I said, there's a key on your calculator for that purpose. And that's one reason why we do it this way. So it's certainly easy enough using 5 and 4 to just multiply them together. But let's say you have 100 shapes and you want to pick out 20 of them. Do you really want to multiply 100 times 99 times 98, etc.? You certainly don't want to do that. It's much easier just to use a simple n permute r button on your calculator and enter in those two numbers than it is to try and actually do the multiplication on it. And that's why we created this function. So we have a more formal way of noting it, and we can use the formula. You can use your calculator button, however you want to go about it. So the number of permutations of n distinct objects taken r at a time without repetition is given by this formula, but how we typically say it is n factorial divided by n minus r factorial, which if you look at up above in our example, n factorial is the 5 factorial. We chose 2, so r is equal to 2. 5 minus 2 is equal to 3, so 3 factorial was in the denominator. This is exactly what your calculator does when you do this permutation. And these can get large fast. These are very large numbers. They get very large very quickly. As an example, and I'm going to do most of this using my calculator, but if let's say we want to pick out of 30 possibilities, we want to pick 4. So we want to 30 permute 4. That would be 30 times, so for our first choice, we have 30 possibilities, then 29 possibilities, then 28 possibilities, and 27 possibilities. Now that's not too bad to multiply, so let's go ahead and do that. 30 times 29 times 28 times 27, and that gives us a rather large number, 657,720. On the other hand, we can just plug this into our calculator, in which case it would be 30, and then you use the calculator button, permute 4, which gives me the exact same answer. Combinations. So we're going to talk about combinations now. Now, a combination you would think is a little bit easier than a permutation. So a combination is when the order doesn't matter. So for a permutation, the order matters. The order in which you make your selections matters. For a combination, the order doesn't matter. So this is basically choosing with replacements, but you want different items. So, and we'll see how this works out. So the question, starting with the same 5 shapes, is how many different combinations of 2 of them can we choose? So you could pick one, and then you could pick another one. So you're still choosing 2 different ones, so 5 times 4. But the order doesn't matter. So you could pick them in the other order, and that would be totally fine. And I'm not going to go through the derivation of this. It is in the book. So if you really want to see it, how this derivation comes about, you can look it up in the book. I did show it for the permutations because it's very easy, follows very clearly and easily. This one's got a little bit more to it. So how we denote this is a combination of a set of n distinct objects taken r at a time without repetition, is an R element subset of a set of n objects, blah, blah, blah. Okay. Anyways, the arrangement of elements in the subset doesn't matter. We denote this by n, and how we typically say it is n choose R. So previously we said n permute R. Now we're going to say n choose R. So the number of combinations of n distinct objects taken R at a time without repetition is given by this formula. And this notation that you're seeing here is a standard notation. So you're going to see n choose R. This basically means exactly, both sides of this mean exactly the same thing. This is n choose R, and this is n choose R. What it works out to be is the number of permutations n permute R divided by R factorial. But you have a button on your calculator, and I recommend you use it. And R has to be less than or equal to n. It cannot be greater than n. R must be less than or equal to n. How do we use this? Let's try some examples. Combinations. So choose 2 of 5 shapes. Let's just use the formula and then also use the combination key on the calculator. Generally speaking, we're going to use a combination key, but let's use the formula. So we're going to do 5, choose 2, and that equals, and we're going to use the permute button on our calculator. You could always work it out to be the formula if you wanted. 5 permute 2 divided by 2 factorial. 5 permute 2 is 5 permute 2, which is 20, divided by 2 factorial is 2, it equals 10. Using the button on the calculator, we have 5, choose 2, and that equals 10. So make sure you get comfortable using the buttons on your calculator. We will see this in probability, and here's an example of why. So let's try this. A company has 7 senior officers and 5 junior officers. So there's 7 senior and 5 junior. And it wants to make a committee. So how many 4-officer committees? So there's 4. So we're choosing a total of 4. But we want 4-officer committee. We want 1 senior and 3 junior. So basically, we want 1 from here. So we're 7, choose 1, multiplied by, and then we have 5 to choose from, so 5, choose 3. So this is the number of combinations that are possible from the senior officers, and this is the number of combinations that are possible from the junior officers. And then we just multiply those together. And that will give us 7 times 10, which equals 70. Let me see what the next problem. How many 4-officer committees with 4 junior? So now we just want a 4-officer committee with 4 junior officers. And that is straight up 5, choose 4, 5, choose 5, choose 4 is equals 5. So using just junior officers, we can make 5 committees. How many 4-officer committees with at least 2 junior officers? So now we want junior officers to be greater than or equal to 2. So this is a little bit more complicated. How do we go about that? Well, junior officers have to be greater than or equal to 2. So that means we can do a committee that has, and this is a 4-officer committee, so you can have 1 senior and 3 junior. 2 senior, and 2 junior. And junior has to be greater than or equal to 2. So those are our 2 possibilities, because if when we go to the next one, we have 3 senior and 1 junior. This is not okay. So this is one set of combinations. This is another set of combinations, and these get added together. So 1 senior officer. So we're doing 7, choose 1, times, and this is just for the set. So times 5, choose 3. So this is how many ways we can do this first combination. So this is one of our possibilities. The other possibility is we can have a committee that's made up of 2 seniors and 2 juniors. So that is an additive, not a multiplication. So then we can do 7 choose 2 times 5 choose 2. Let's verify that we have all of this correct. So what we see is 7 choose 2, 5 choose 2, so plus. Oh, I guess I did forget. I forgot a possibility. I could have a committee with 0 senior officers and 4 junior officers. I forgot that one. So plus 5 choose 4. And that will give me 21 times 10 plus 7 times 10 plus 5, which is equal to 285. So when you're going through the possibilities, at least, so we have to have at least 2 junior officers, 2, 3, and 4 are acceptable. And that ends part 2 of our lecture 10. Thank you for joining me.